next unit we're going to look at is a revision of the GCSE topic around the mole. Okay, so these are the learning objectives for the unit. It's your job to go through them, tick them off as you go, and if you are struggling with them, to come and see me, so we are all on the same page. Right, so the first thing you have to do with the moles and the ideas around the mole is be able to convert between units. Okay, so from the very large, like mega, 10 to the 6, to the very low, like nano, 1 times 10 to the negative 9. You have to be familiar with both the subscripts, the superscripts, the 10 to the 6, 10 to the 3, also the prefixes like mega, kilo, centi, and milli, and also the symbols that are used for each of the prefixes. So conversions may seem obvious at the start, for example, converting decimeters cubed to centimeters cubed, which you would have done in your practical, but you need to have a develop a method when you're developing harder equations and that are coming with solving stoichiometric problems. So big issue with students missing out those final marks is the conversion of the units is not correct. Okay, so as an example, let's convert 9 nanometers to centimeters, giving 1 nanometer is 1 times 10 to the negative 9 centimeters. So we've already been told that 1 nanometer is 1 times 10 to the negative 9 centimeters. Okay, so we'll make 9 nanometers x. Okay, and therefore by cross multiplication, x times 1 nanometer will give 9 nanometers times 1 times 10 to the negative 9 centimeters, which will be 9 times 10 to the negative 9 centimeters as the value for x. Okay. If you're dealing with a unit change, when you're cross multiplying ratios, this is an example here. So converting 530 calories to joules, so you're converting calories to joules. You're usually given that the 1 calorie is 4.18 joules. Okay, so 1 calorie, 4.18 joules. So therefore 430 calories can be x. So by cross multiplication, x times 1 calorie equals 530 calories times 4.18 joules. So it's going to equal 2,215.4 joules. Okay, and due to significant figures, 2,200 joules. Okay, so the mole. This is the crux of the topic. So the mole is a very large number, 6 times 10 to the 23. Yeah. And the number is called Avogadro's number. Okay, when we use this number to count things in chemistry, because we deal with big numbers like number of atoms. And because we are lazy, we drop the E, so mole can be abbreviated to mole. And lowercase n is the symbol, and it's used to represent the number of mole. Okay, so this is what you should be familiar with. Capital N is a number of things, could be ions, atoms, molecules, formula units, and electrons, or motor cars if you wanted to be that way inclined. Lowercase n is number of moles, and 6.02 times 10 to the 23 is Avogadro's number. And we can use these values to calculate different things. So here's two examples here. How many atoms are there in 1 mole of water, and how many moles are there in 12 times 10 to the 23 atoms? So pause the video now and then come back when you think you have an answer. Okay, so the answers hopefully are water has 3 atoms, so therefore it's going to be 3 times 6 times 10 to the 23, or 1.8 times 10 to the 24 atoms. And how many moles are there in 12 times 10 to the 23 atoms? It's essentially number of atoms divided by Avogadro's number to give 2 moles. Okay, so in terms of molecules, how many molecules are there in 4 moles of water, and how many moles are there in 12 times 10 to the 23 molecules of water? So again, pause the video, see if you can come up with an answer, and then play it again when you think you have the correct answer. Okay, so welcome back. So hopefully you would have got the answer as being, for the first one, 2.4 times 10 to the 24 molecules. Okay, so it's going to be basically Avogadro's number multiplied by 4. And number of moles is going to be, again, number of molecules divided by Avogadro's number. So 2 moles of water molecules. Okay, so for ions, how many H plus ions or protons are there in 2.5 moles of hydrochloric acid solution? And how many moles are there in 14 times 10 to the 23 protons or H plus ions? Again, pausing the video and coming back to it later. Okay, so let's see if you got the right answer for these two. So hydrochloric acid completely dissociates with H plus in water, or the form H plus in water. Therefore, it's going to be 2.5 times Avogadro's number, or 1.5 times 10 to the 24 ions. And then the final answer, 14.0 times 10 to the 23 divided by Avogadro's number gives 2.3 moles of H plus ions in that solution. Okay, and finally, electrons. How many electrons are there in 1 mole of helium, and how many moles are there in 14 times 10 to the 30 electrons? Again, pausing the video and seeing if we get the right answer. Okay. So again, welcome back. So how many electrons are there in 1 mole of helium? So looking at your periodic table, you should know there is 2 electrons, so it's going to be 2 times Avogadro's number, or 12 times 10 to the 23 electrons. And how many moles are there in 14 times 10 to the 30 electrons? Is going to be, again, dividing it by Avogadro's number, 2.3 times 10 to the 7 moles. Quite a number of moles. Okay. The last one to look at is formula units. So you may not be familiar with this from last year, but you should have used it with ionic bonding. But how many formula units are there in 1 mole of sodium chloride? And how many moles are there in 1 times 10 to the 30 formula units of sodium chloride? Okay, so you should have got the answer as being 6 times 10 to the 23 formula units, because sodium chloride is the formula unit for salt. That's the simplest ratio of the ionic compound. And how many moles are there? And 1 times 10 to the 30 formula units. Okay, so it's going to be 1 times 10 to the 30 divided by Avogadro's number, which is 1.7 times 10 to the 6 moles. Okay, so an important part of stoichiometry is the idea of relative masses, which you should have touched on last year. So relative atomic mass, AR, is the mass of an atom relative to the 12 carbon isotope having a value of 12. Okay, so AR is the average mass per atom of element divided by the mass of one atom of carbon 12 times 12. Okay, so magnesium is 24 divided by 12 times 12. Okay, so 24 is the AR. The relative isotopic mass is going to be similar, but uses the mass of the isotopes instead. Relative molecular mass is when you're adding the atomic masses, okay, to get a molecular mass. And finally, the relative formula mass is to do more with ions and other species around ionic bonding. Okay, so example, sodium chloride and hydroxide ions. Okay, so with that in mind, what is the relative formula mass of sodium chloride, and what is the molecular mass of water? Okay, so you should have got the answers of 58.44 for the MR of sodium chloride, noticing of course that it is unitless because it's relative, okay, simply by adding the relative atomic masses of sodium and chlorine together to give the relative molecular mass of sodium chloride's formula mass. And the relative mass of water is going to be 18 because you've got 2 oxygens, 1 oxygen, 2 hydrogens, so 2 plus 16 gives you 18. Right, so molar mass is something which will be introduced this year in IB. You touched on relative molecular mass, but molar mass, also known as atomic mass or formula mass, has units of grams per mole and is written as grams per mole to the -1. Okay, and if you look at the periodic table, this is what the molar mass, this is what the masses of the atoms are calculated in. So, for example, the molar mass of carbon is 12.011 grams per mole. Okay, so the number of moles, lowercase n equals the mass, which is lowercase m, divided by the molar mass, which is the big M. So little m divided by big M gives n number of moles. Okay, so remember the formula, how to substitute using the formula, and also the units of the formula. So using that equation, how many moles are there in 1 gram of sodium chloride? Okay, so pause the video now and then come back to it later. Right, so what you should have found was the molar mass was the first thing to be calculated, which we've already discovered in the previous slide, which is 58.443 grams per mole. Noticing now it has units because it's now molar mass. Okay, the mass of sodium chloride is 1 gram. Therefore, the number of moles of sodium chloride is going to be little m over big M, or 1 divided by 58.443, which will give you the number of moles, 0.0171 moles of sodium chloride. Okay, another question, or this is an example now. How many grams are there in 2 moles of water? Okay, the answer's up, so we can't really go through it in that sense. But you can see the answer is 36 because you've got, again, molar mass of water is 18. So you rearrange the formula to give the mass equals number of moles times molar mass. So it would be 36 grams of. The general strategy is to first convert the moles unit, use the ratios in the balance equation, convert them back into the moles unit. And we're going to do some more examples. First, we'll start with solids, okay, because that's probably what you're more familiar with from last year. Okay, so the first thing you've got to do you've got to find the mass of A using the number of moles. Okay, so usually you're given the mass of A. You convert that into number of moles, use the equation to find the ratio of mole A to mole B. You can then plug that into the equation of N times big M to give finally the mass of B. That's how the strategy is to work out the mass of an unknown if they are solids, or if you've given the mass of a solid. Okay, so here's an example of a problem. You have 184 grams of this exotic oxidizing agent, and it's decomposing into potassium chloride and oxygen. Okay, so the question is how much grams of oxygen are produced. Okay, so pause the video now and then we'll go through the answers very soon. Okay, so welcome back. So let's go through the answers now. Okay, so we're going to work out the number of moles, okay, of the solid, which is going to be little m over big M. Plug the numbers in, and you get 1.5 moles. From the equation, okay, you have a ratio of 2 to 3, so 1.5 to x, which we want to find out. So x is going to just basically be calculated for the ratio to be 2.25 moles. So the mass of oxygen is going to be number of moles of oxygen times its molar mass, which will be 72 grams of oxygen. Okay, so hopefully you got that right. If not, here's a second problem. Again, with the same kind of chemistry, how many grams of KClO3 is needed to produce 205 grams of potassium chloride? And you've been given the equation. So pausing the video again and seeing what the answer is. Okay, so this is hopefully what we'll do it stepwise. Okay, first thing I'll do is work out the number of moles of potassium chloride. So it's going to be little m over big M. So it's 2.75 moles. You have the equation, so you have a ratio of 2 to 2 or 1 to 1. So 2.7 moles of potassium ClO3 are produced. So that means that you just have to plug that into the equation of mass equals number of moles times molar mass, which gives you the answer of 337 grams. Okay, so that's molar calculations to work out unknowns and experiments. Also, percentage composition is important, and it's basically the amount of each element in the compound expressed as a percentage. Okay, so I'll illustrate it in an example of a problem. So what is the percentage composition of sulfur in sulfur dioxide? So let's see if you can work it out first, and then we'll go through it together. Right, so basically the molar mass of sulfur dioxide is 64 grams per mole, which you can get from the periodic table by adding the atomic mass of sulfur and the atomic mass of oxygen. And then the molar mass of sulfur again is simply 32. So the ratio or percentage is going to be 32 divided by 64 times 100. So basically 50% of the weight of sulfur dioxide is actually found in the sulfur. Okay, so empirical and molecular formula. So the empirical formula is a compound is defined as the simplest whole number ratio of atoms of different elements in a compound, whereas the molecular formula of a compound is the actual number of atoms of different elements covalently bonded in a molecule. And the two can be the same. So for example, you can have an empirical formula of CH2, but they can be different molecular formulas, okay, which we'll illustrate on the next slide. And water is both the empirical formula and molecular formula for water. So here's the example here. We have two different alkenes, differently substituted, different number of carbons. They have the same empirical formula, but because they have different number of carbons and hydrogens, they have a different molecular formula. Okay, so how do we determine empirical formula? So what we do is we pretend we have 100 grams of the sample, and then we change that percentage to grams, convert grams to moles, and then write the number of moles as a subscript of the chemical formula. Okay, divide each number by the smallest number and multiply the result to get rid of any fractions. Okay, so we're going to go through an example to actually illustrate this point. Okay, so the first problem is calculate the empirical formula of the compound composing of 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. So again, pausing the video, let's see if you can work it out first, and then we'll go through it together. Okay, so welcome back. So this is how we do it. So again, we're assuming 100 grams, so the number of moles of carbon will simply be 38.67 divided by 12. Number of moles of hydrogen, 16 divided by 1. Number of moles of nitrogen, 45 divided by 14. So you get these you get these numbers of moles of carbon, hydrogen, and nitrogen, okay, which we see here. Okay, so then we divide by the smallest number, which is just nitrogen. Okay, we get a ratio, therefore, after we've done that, of carbon 3.22. First thing we've got to divide by all these numbers. That's on the next slide. Okay, so we get this ratio at the moment of carbon 3.22, hydrogen 16.09, and nitrogen 3.219. Okay, then we start dividing by the smallest number, which of course is the nitrogen. Okay, so by dividing by the smallest number of nitrogen, we get 1 mole of carbon, 5 moles of hydrogen, and 1 mole of nitrogen. So the empirical formula becomes C1H5N1. Okay, so let's see if we've got this down pat. A compound is 43.64% phosphorus and 56.36 oxygen. What is the empirical formula? So again, pausing the video and we'll go to it. Okay, let's see if we've got the right answer. So again, converting to 100 grams, dividing by the molar mass, we get 1.4 moles of phosphorus, 3.5 moles of oxygen. Ratio is 1.5 roughly to 3.5. Obviously you can't, those aren't whole numbers, so you need to divide it by the smallest, which is your 1.4, which is P1025. Again, 2.5 is not a whole number, so got to multiply by 2 to get the empirical formula of P2O5. So that's empirical formula, and you can use it now to determine the molecular formula. Since we have the empirical formula being the lowest ratio of an actual molecule, it would weigh more by a whole number multiple. So if we divide the actual molar mass by the mass of 1 mole of the empirical formula, we can start determining a ratio which we can then determine the molecular formula by, which we're going to illustrate in the next slide. Okay, so this is the worked example. Caffeine has a molar mass of 194 grams per mole, and empirical formula C4H5N2. So what's this molecular formula? Well, we work out something called X, which is kind of the common ratio, which is going to be the 194, which we get from the question, and 97, which is going to be the mass, and and this should all be in grams per mole, okay, and that's going to give you 2 times the actual empirical formula, because you get a ratio of 2. Okay, so it equals 2. So that's going to be the molecular formula, twice the empirical formula. Okay, so problem 2. So this is the final slide for today. Let's see if you can do it for yourself. Okay, so a compound is known to be composed of 71.65% chlorine, 24.27% carbon, and 4% hydrogen. The molar mass is known, and it's known to be 98.96 grams per mole. Oh dear. And what is the molecular formula? So pause the video now and see if we get the right answer. Right, so let's see if we've got the answer. So again, first thing we're going to do is the empirical formula. This is what this part here is. So you're converting to 100 grams, dividing by the molar mass of each of the atoms associated. So you get a 2 to 2 to 4 ratio. We divide by the lowest, which can either be the carbon or chlorine. That's up to you. So then we get C1Cl1H2 as the empirical formula. Okay, that's your empirical formula. And the molar mass will give an empirical mass of 48.5. So we basically find the mass of that guy, and we then find the ratio. So it's going to be 98.96 divided by this number here to give you 2. So you just multiply the empirical formula by 2 to get the molecular formula. And that is the answer.